Morning, everyone. So yesterday we started into our organic chemistry chapter. It was an area of chemistry here focusing on molecules that are based off of carbon. We started learning some of the prefaces that end up forming the parent, methyl, ethyl, propyl, those prefaces there. We started introducing towards the end of the lesson the fact that the carbons don't have to strung together in one long chain. We can actually have branches off the trunk of the parent. And our starting way of naming the structure here is to try to find the longest string of carbons we can get. So let's start off with one of those examples here, and then we'll deal a little bit more with branching today. The temptation to fight here is it's not always going to be the left to right here. That's always going to be the longest chain. So there are some questions in your worksheets here that sort of try to trick you, and they try to say, oh, is this one here? Let's say if I went left to right here, just as an example molecule here, well, we have 5 carbons in a row. Is this a 5-carbon parent with a bunch of these chains that are sort of branched off? I have a 3-carbon branch, 1 carbon, a 5-carbon branch that way. Or better yet, again, we could start from any side to any side here. Let's see if we can string together the absolute longest number of carbons that we have. This is actually the most important first step because we want to figure out which part is the trunk of it. If I get the trunk wrong, I may accidentally be calling some of the branches the trunk or vice versa. So if you just take a look at that here, string together as many carbons as you can. Again, with more practice, you can sort of spot longer chains easier, but it is just a little bit of trial and error. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. All right. You should be able to actually tell me, wait a second, if I go from this side to the very far side, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, even 11, right? So we actually only did prefaces up till 10, okay? Well, there are longer alkanes like that, okay? But here we have 11. You'll notice by actually recognizing the correct parent, it actually, well, this orange that we did before, yep, these orange parts here were actually part of the carbon, but earlier when I had named these other side carbons here as part of the parent, no, they actually aren't part of the parent. These ones here are actually branches that are branched off of this green parent there. So just to start you just thinking here, always making sure you have the longest carbon chain before I start naming some of these alkyl groups. We're going to see a little bit more of the branching and what if I have the same branch and different branches and different positions like that. We'll see all those rules a little bit more in today's lesson, but for starters, at least find the longest parent. All right? So we have that as a parent here. We're going to start doing some branching as we alluded to here. In general, we're going to start calling these ones here alkyl groups. So alkyls, these ones here essentially refer to branches or branching. There's going to be 2 main types of branches that we look at here. The branches that we've seen so far are carbon branches. So if I just say just a general alkyl group here, these are going to be carbon-based branches. So I can have CH3, CH2, those kind of branches off of the parent, okay? Towards the end of this lesson here, we're going to actually throw on some halogens as well. Halogens are your group 17 or group 7, the fluoro-chloro-bromo-iodo. Those could also substitute as branches like these carbon branches are. Fortunately for us, they sort of follow the same rules as these alkyl branches do. All right? So let's just start off here. Let's just string together a bunch of carbons here. We'll make it as long as before. All right? And let's, okay, there we have a 7-carbon parent. Let's sub on, let's say, C there, maybe a C over here, and a C over here. Okay. This is a Lewis diagram, so it isn't super important sort of which side I'm showing this molecule. We're going to see actually, because these are single bonded, they actually twist no problem. If I built this with a model set here, you can rotate these molecules here, definitely no problem. Okay, but I've given you the backbone, I've given you the main structure here. Again, let's follow our rules. If you've forgotten here, again, first, find the longest carbon chain. This becomes your parent. Right? Again, there's no one right way of doing it. You just do it by trial and error. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4. You just want to find the longest carbon chain. Once you find it, I would just encourage you just to circle it. Okay. So in our case here, we have a 7 chain. Okay. The prefix for 7 is hept. So this is going to be the very last word or name. It's going to be blah, 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 heptane. Hept for 7. A and E tells you that we're in the alkane family, single bonded family. Heptane would have just be these 7 carbons saturated with the rest hydrogen. You'll notice I haven't drawn any of the other hydrogens. I know these carbons here aren't radicals. I know they don't actually hold on just to unpaired electrons. I know that the hydrogens actually saturate the rest. There's hydrogens that sort of fill up all the gaps here. This carbon here already has 3 attachments, so I'm going to glue another hydrogen on top of there. Sometimes I even shorthand, almost like condensing the number of hydrogens on there. But it turns out for us here, the hydrogens don't change the name, so we're mainly focusing on the carbon bits anyways. So just for simplicity here, it is understood that the carbons do have enough hydrogens to sort of saturate off the rest. I'll just put little dots for you there. But at the very least here, the naming that we're going to see here, it's only based on the carbon parts of it. All right. So what's circled here is this word here, heptane. Okay, it's a 7-carbon chain. The parts that I haven't circled, I still have to name. Again, I imagine that the rest of the branches are hydrogen, so I don't need to name those parts. But there are a few places that I would have expected the carbons holding hydrogen, and yet I pulled off the hydrogen that was here, and I actually put on a 1-carbon branch. Again, just for the branch itself, this is an alkyl group, this is a carbon branch. We're going to use the prefix here, meth, for 1. Because alkyl group has the ending YL, instead of, again, calling it methane, heptane, we're going to refer to this here as a methyl group. It's a 1-carbon branch. This one here, similarly a methyl group. This one here, a methyl group. You'll notice I can have multiple of the same branch here. Totally no problem. Okay. So we have 3 methyl groups here. But again, this 7-carbon chain here is nice and long. So I want to just sort of imply, well, where along this parent here have I started making these substitutions? These substitutions don't happen just by chance. They actually need to be chemical reactions. You physically need to come in, actually break apart a bond of C and H, and then glue it back together with CH3. So it doesn't spontaneously happen, but just for simplicity here, yeah, we've just substituted, we've sort of, in place of the hydrogen, we've replaced it with a carbon group. So I have a bunch of these methyl groups here. There's actually 3 of them. Okay, so here are sort of 2 side rows that we're going to start seeing here. We have 3 methyl groups here. We need to number the parent so that the methyl groups occur at the smallest numbers possible. The numbers only apply to the parent, so I can either number it top down. So 1, 2, 3, 4, 5, 6, 7. In that case, my parent would be at position 2, there's a methyl. Position 4 is my second methyl group. Position 5 is going to be the next methyl group here. So I'm playing around with the number set here, 2, 4, 5. What if I numbered my 7-carbon chain the other way? What if I went 1, 2, 3, 4, 5, 6, 7? Well, then, looking at it that way, my same chains would have occurred at position 3, position 4, and position 6. All right. If you remember from yesterday here, we do our best here, and we always try to keep the numbers as tiny as possible, okay? So keep numbers, these are the branches, okay, as small as possible. So I know in general the 2, 4, 5 are tinier than 3, 4, 6. Really, it's only the first position that's different. That's where we're actually going to make the difference already. So between 2 and 3, hey, 2 is a tinier number, so I'm not even going to consider this way here, okay? So I'm going to prefer to count it top down, this sort of red colorway here, so that my branches occur at 2, 4, 5 instead of 3, which would be a longer way of counting it. Lastly, I need to do, separating numbers and the name of the branch here, I go number hyphen the branch. So in this case here at position 2, I have a methyl group. So I have a 2-methyl. I happen to have at position 4 another methyl group, 4-methyl. So far I'm just starting with just plain old methyl groups here just for simplicity. We have a 5-methyl groups. You're starting to see this name here get really long really quickly. That's just because I have multiple branches I need to name for you. I have a methyl. Every one of these words here, methyl means a 1-carbon branch, a 1-carbon alkyl group. And all I'm doing is I'm spotting for you here where along my parent does that end up showing up. At spot 2, at spot 4, spot 5, I happen to be subbing on another methyl branch. And in this case here, we're going to end off with the parent name. We already named it in the earlier step here. Usually the very last branch and the parent, we just ram it together, almost like one word together, methylheptane. So we would have just been a heptane, we would have just been 7 carbons long, except at these 3 special spots, I have now substituted my alkane. So let me just give you that name here. Sometimes they say, name the substituted alkane. I've replaced a few spots that have would have been H's. I've replaced them with carbon branches. Now, IUPAC came along and said, well, I already see that this name is getting really long really quickly. Is there any way I can start simplifying this? Make this a little bit easier. Well, let's try it out here. Seeing as these methyl branches here are all identical, what we can actually do, we'll add on one sub rule that we're going to see in this example. If we have multiple of the same branch, so in this molecule we see we have a bunch of methyl groups. We actually have 3 of them. If you have multiple of the same branch, what you're going to do is you're going to actually revert back to the regular mono, di, tri, those prefixes we did earlier. Well, since I have 3, the prefix for 3 is going to be tri. Instead of naming these methyl branches really, really detailed and whatnot, just a little bit long, I would like to sum this part up if I can. I'd like to sum it up here as a trimethyl. Okay. The tri tells you we have 3. We know that prefix from before. We have 3 of the same methyl branch. We have 3 of the same 1 carbon branch. Right? They're identical. So that saves me the hassle of writing 2-methyl, 4-methyl, 5-methyl. Okay? But we have 3. I still need to imply where they are though. So where they happen to be were 2, 4, and 5. Since I'm sort of condensing that down a little bit here, numbers and numbers are always separated just by commas. So as I was doing earlier here, 2, 4, 5, hyphen trimethyl. The trimethyl just tells me right away there's 3 methyls somewhere in the picture, but we actually still need the spots. One's at 2, one's at 4, one's at 5. That's exactly what we've drawn previously. So this is one extra rule here. If you happen to have many of the exact same branch, that's where we start getting our mono, di, tri, tetra back. That sort of condenses me from having to write it out a couple of times, and then we still end up with the name here, heptane. Right. That's what you do if you have the same branch. Right? So nice and easy there. Okay. Let's try another example. What if my branches start getting different? Okay. What if there are all methyl groups? What if I have some ethyl groups and other different groupings come into play? So let's see if I can string together a bunch of other carbons here. Try to just give you a little bit of variety. Usually if you're just sort of watching me sketch it here, usually I do tend to draw the parent first. But nonetheless here, if you didn't really spot that, you can still just find the longest chain, one side to the other side. Right? Sort of drew this sort of twisted in on itself here. Okay. So take a second there, see if you can find the longest carbon chain. This is going to have a little bit more than what we had before. Okay, it's going to have a couple of similar branches. We're going to a couple of different branches, and we're going to see what's the naming rule in that situation. So again, I do understand that the rest of these have hydrogen. So this carbon only has 1 carbon neighbor. So there's 3 hydrogens there. That has 1 and whatnot. Okay, but it turns out those hydrogens don't really change the name. So that's why I haven't really drawn them all in. Okay. Our starting rule, like we said, was to find the longest carbon chain. So from any side to any side, okay? Let me just try it here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? So a couple of different choices you can do for 8. Okay. This one here, strangely enough, I'll draw you the 2 8s for you here. If I draw these 8 carbons, so you're going from one side to the other side, this way of counting the 8 here is actually a little bit easier because you actually see the branches are branched directly off my green carbon trunk. It's also possible you could have labeled, let's say, this as your 8 carbon trunk. Right? The rule just said find the longest carbon chain. What if I have 2 ways of counting 8? Technically, we should end up with the same name, but this example here is actually a little bit more complicated here. I would actually choose the green way versus the blue way. With the green way, I have all the branches branched off the green parent. In this blue way, we're starting to get some complexity here. This branch is now a little bit crazy. This branch, sure, I'm branching off at, let's say, 3 carbons in on this side here, but this branch also has another branch to it. It's like a branch on a branch. Now, sometimes in organic, we do have to deal with a situation, branches off branches, alkyl groups off alkyl groups. But in this case here, seeing as I had a choice, just to simplify things, let's just revert down to the 8. So we actually have all the carbons branch off the single parent. So that's our parent. The parent is going to be the very last word in our name. So 1, 2, 3, 4, 5, 6, 7, 8. We're going to be an octane. Oct stands for 8 carbons. We're still in the alkane family. We will be for a couple of days yet. The octane word here covers everything in the green circle. We now need to name the other parts that I haven't circled yet. So we've seen these two groups earlier. We saw a carbon branch. Just the branch itself has 1 carbon, so we'll call this a methyl branch. Just this side here has 1 carbon. That is also a methyl branch. Okay, so I have 2 methyls that would end up being a dimethyl later on. Okay, and here we're going to start seeing, oh, this branch by itself actually already has 2 carbons. It's not part of the parent, but we've dealt with this before with prefaces. Meth meant 1, so eth actually means 2. Again, we don't say ethane, octane, we say ethyl, right? So just like we name for our parent, the number of carbons that we string together is what prefix that we end up using. One last rule here is when we're counting the parent chain, we always want to count it so it's the smallest number as possible. So just counting it. If I count it bottom up, 1, 2, 3, I have a branch at 4, a branch at 6, a branch at 7. Okay. Or if I count the parent going top down, I have 1, oh, my branch is already at 2, 2, 3, and 5. Well, having a first branch at 2 is better than having a first branch at 4, so I'm going to prefer to count it top down. Remember, this sort of captures the fact, what if this molecule has twisted on itself? What if I'm looking at it from the opposite side? As long as I try to keep the numbers as tiny as possible, we should always end up with the same name. So here's an example where we actually have multiple different groups. So one last rule for this one here. If we have different groups, like in this case here, we have a methyl, 1 carbon branch. We have ethyl. In this case here, what we're going to do is we're going to alphabetize the branches. So if you have a choice, okay, just do your ABCs, okay? E for ethyl is going to come before M for methyl. All right. Now I want to just emphasize the fact here, when I count it down this way here, having this set, oh, the first branch is at 2, and then the next branch is at 3, I've already made sure the numbers are tiny. We're going to see, though, based on this alphabetizing rule, sometimes the numbers in the word name are actually out of order, just because of the letter of the branch where it actually came on the parent. So E for ethyl comes first. It is branching off at position number 3. I can say 3-ethyl. Again, numbers and letters are always separated by hyphens. We should actually say, well, at position 2, position 5, there is a 2-methyl, and there is a 5-methyl. But we saw this in the earlier rule here. Wait, if I have 2 of the same methyl group, why don't I just call that a dimethyl, and why don't I just put the numbers in front? So the final name for this part here would actually be, we'll still have our 3-ethyl. We'll have a hyphen to 2, 5, a dimethyl, and it's going to take a little bit of practice. And all that is substituting off an 8-carbon alkane, okay, an 8-carbon octane there. All right. Now, again, when you start looking at this one here, you're going to start worrying, wait, how come the numbers aren't smallest, okay? Well, we already made sure 2, 3, and 5 were tinier numbers than counting it the other way. It would have been 4, 6, 7. The only reason why these numbers are out of order are because we had prioritized E comes earlier in the alphabet than M for methyl. So even though the numbers are tiny, the IUPAC name, the word name, sometimes has the numbers out of order, just depending on which branch is branching off at which position. The one other thing that we might end up seeing is sometimes if you have multiple of the same branch and they also occur at the same number, you do also want to repeat the same number of numbers. Okay, let's say I have 2 methyl groups branch off carbon number 2, I'd still go 2, 2 dimethyl. And we'll see that a little bit with the next example. I should have the exact same number of numbers to match up how many of that branch that I have. And you'll notice for the alphabetizing rule, sure, I actually called up a di or a tri from the earlier example here. I don't alphabetize it based on the D for the di. I alphabetize it based on the branch name. So M still comes after the E. All right. Let me throw on just one extra layer of complexity, and then we'll just do a little bit of practice here. So far, we've been looking at these alkyl groups, alkyl branches. Alkyl groups in general have been carbons. We can actually get a slightly different family here. We'll call these alkyl halites. Now that word halite, I mentioned to you earlier here, we're actually subbing on halogen groups. We're subbing on things like fluorine, chlorine, bromine, and iodine. So it doesn't all have to be just plain old carbons and methyl ethyl groups like we've been playing around with. We can actually sub on these halogen groups. And just to distinguish them a little bit from the earlier branching we had YL as an ending. For these halogen groups here, we're actually going to say, instead of fluorine, we'll say fluoro, Cl, we're going to say chloro, Br, bromo, and then I, we have iodo. So just the ending O, okay? Still a branch, we still want to keep the numbers tiny, we still alphabetize, everything else is normal, but what we're allowed to do here is we're actually allowed to start subbing on some halogen groups. So let's just do a little bit of practice here. It's funny, on quizzes and tests for this, I do give people, you can have the periodic table if you want. Well, we're doing naming. Why do I need the periodic table? I just name the parent, name the branches, and whatnot. It really is funny enough. Well, if you're doing fluorine, make sure you know the symbol for fluorine is F. Or chlorine, make sure the symbol is Cl. Sometimes people accidentally just write C or FL for fluorine, things like that. Just make sure you write the right symbol, but nonetheless, they are just simple branches. So let's start off with a couple of carbons here. Keeping things simple here, I'm just going to draw it left to right. Okay. Unlike a methyl group, okay, unlike a carbon branch, where previously here, if you try to sub on a methyl branch, let's say on the end, this is not a hexane with a methyl branch. If I just string together the number of carbons, this is just 7 carbons in a row. If I put this methyl group here on the front, it also is just 7 carbons in a row. So this isn't a methyl group at all. For carbon-based branches, they can't be on the sides of the chain. Carbon-based branches here can be anywhere mid-chain. So this one here is actually a methyl branch because this can't extend to the parent. We don't have the same restriction to these halogens though. So for example, if I have halogen, let's say a chlorine, although the lettering here also looks like C something, okay? Chlorine is not carbon, so when I'm counting the parent, I would not count 1, 2, 3, 4, 5, 6, oh, there's a C, 7. That's not a carbon. So chlorine here actually has a little bit more flexibility here. It doesn't actually have to be on just the middle of the chain. It can appear anywhere. I can have many of these groupings here. Let's pop on a chlorine here, and maybe a chlorine over here as well. Let's even sub on one last group. Let's say a fluorine maybe. Okay, this would get really complicated really quickly. Okay, let's sub on a maybe an iodine group, just to give you a sense that there could be other things that are attached to this alkane. Now, one thing I do want to imply here, you'll notice if I have a methyl group, normally I just show it as a single bond to a carbon. Hey, we're carbon, we should be able to see where all 4 bonds or carbons are. We're going to just assume that the rest of it is saturated with hydrogen. This is not true with these halogen groups. These halogens, certainly they have electrons around it, but as a halogen, they're not carbon. They don't have unpaired electrons. They are not saturated. It's not chlorine holding on another hydrogen. No, there's actually nothing attached to them. They actually just have lone pairs on the side. So that's one other difference here. Aside from that, we've actually done this naming before. Let's see if we can practice this. Okay. If you want to just pause the video for a second, give it a try. Okay. Assuming you've done that here, first step, find the longest carbon chain. Okay. You can go from any side to any side. Just for simplicity here, I kept the longest chain here just in the middle. Usually I just circle the longest carbon chain. My parent here has 6 carbons in a row, so you can look at your prefix here. Prefix for 6 is going to be hex. So the very last word in our name is going to be something hexane, a 6 carbon, single bonded family. Hexane would have just been 6 carbons all in one long row. It would have just been saturated the rest with hydrogen. Whatever I haven't circled yet, I still have to name. This group here is a 1 carbon branch. You've seen it a couple times now. We have a methyl branch. Now we started adding on some halogen groups here. Again, the halogens don't hold other neighboring hydrogens, but you can similarly here call this chloro groups, call these iodo, call this fluoro. Those are also substitute alkanes branching off the parent, but not necessarily a carbon chain itself. Right. Last rule here is we want to keep the numbers tiny. So as I count, let's say left to right, I'm just going to list them for you here. If I count it left to right, I have a branch at 1, 2. I have 2 branches at 4, 5, 6. Going the other way, I'm counting it here 1, 2, 3, 3, 5, 6. Okay, now there's a lot of similarity. I have 1 at 1, 1 at 2, and whatnot. But if you're looking at this one here, let me write it up for you here. Going left to right, I had a 1, 2, 4, 4, 5, 6. Sure, they're different branches and whatnot. Counting it the opposite way here, I had a 1, 2, 3, 3, 5, 6. Okay. If you can't distinguish it based on the first position here, you go to the next position here. Oh, by the third branch in, counting the green way, having something branched off at 3 is slightly less than branching off at 4. So I'm going to prefer to count it right to left in this case. 1, 2, 3, 4, 5, 6. The number goes on the parent, and we should be able to name the rest of the branches here. I have many different branches, so I need to alphabetize. So C for chloro comes first. Counting it this way here, I actually have a 6 chloro. At position number 6, we have a chlorine branched off of it. The next alphabetizing here is F. That occurs at position number 1. Again, no trouble that these numbers may be out of order just because of the alphabetizing. Okay, we already made sure the numbers are tiny. We have, the chloro, I actually had 2 other chloro groups. Sorry, I missed these 2 groups here. So totally you could have gone 6 chloro and then 3 chloro, 3 chloro. But remember, there's 3 of the same group here. We're actually going to change this first part up here. I'm going to say that we have position 3, 3, and 6. So 3, 3, 6. We happen to have a chloro group. Okay. Oh, still missing something. Try to pretend to make some mistakes here for you here. So we actually need a trichloro. Remember, we have multiple of the same group. We always need the mono, di, tri. We still alphabetize it based on C, so that part's still fine. So 336 trichloro, 1 fluoro. Sometimes you can just sort of, yep, got that one, got those ones. The only 2 that are missing are the iodo and the methyl here. I comes before M. I is on position 2. So we have 2 iodo. At position 5, we have a methyl. And then finally, long last, we're going to put this hexane. The parent is always the ending of the name here. Let's just swap that into there. Okay. Again, alphabetizing sake here. C for the chloro, F for fluoro, I, and then M. The numbers are all out of order. There's 3s and 1s and whatever. That was just because of the alphabetizing. And in this case here, because we had 3 of the identical, the same chlorine branch, we had shortened it trichloro, 3 of the same branch. But you notice I still have 3 numbers. Even if they occur at the same position, I'm still repeating that number. If I had just said 3, 6, I don't know where that last chloro is. It on another 3 and another 6? By specifying 3, then 6, I'm actually telling you unambiguously where everything is. Okay. Now that one here was a little bit scary here. I'm going to end off with one last example. So far we've been doing from the structural formula, from the picture of the molecule here back to the word name. You actually need to be comfortable going, if I gave you a long word name like that, see if you can actually rewrite the formula for me. Right? It sounds really scary, okay, but it's actually not all that bad. Okay, so it actually is easier this way. That's what I generally find here. But let's try it out here. Let's solve it on a few different groups. Let's say I have a 3, there's a bromo, 5, there's a propyl. Let's do a nonane. Let's do a 9 carbon chain. Okay. And again, sometimes for the parent name, sometimes I'll just ram it as one word together. Sometimes I'll have a hyphen. Okay. I find chemists are usually lazy. They usually drop this hyphen here. But just to show you, if there's a hyphen there, it's actually not wrong. Okay. That's perfectly fine. Okay. The reason why I'd say it's actually easier going this way, this time it's totally up to you how you want to draw it. Right? So instead of kinking in the carbon chain and twisting it and whatnot, you can, like we did in the previous example, we can do all the carbons in a row in a nonane chain. Nonane stands for 9. We can just string together 9 carbons. We're in the alkane family, so we know that everything is single bonded. Okay? Because counting is totally up to us as well, I usually read left to right, so let me count it going left to right there. Okay. That already covers this nonane part, a 9 carbon single bonded family. I would have understood that the rest of these are holding hydrogens, okay? Except there's 2 spots. At position 3, one of the hydrogens has been replaced by a bromine group. So instead of, let's say, a hydrogen, let's put a bromine. No, it doesn't matter whether you put the Br on the bottom or a Br on the top, because this is a single bond, it's going to twist really easily. Not true for other families. And that 5, oh, we haven't seen a propyl group before. Let's see what we do know. Propane, prop means 3, so we would have had 1, 2, 3. If it were just the parent, propane would be C3H8. If you wanted to do that 2N plus 2, you could have found that easily. But this time, because this alkyl group here is actually a branch, it ends with YL, I need one extra bond to hold on to position number 5. Imagine taking propane, removing one of its hydrogens, and now using this group here. Once I remove the hydrogen, now I'm down to 7. I could either just draw this C3, position number 6. I can easily draw this here as C3H7. Or if that confuses you here, we could also just draw 3 carbons in a row. Because they are carbons, we understand that they have unpaired electrons. Okay, the unpaired electrons are holding on to hydrogens unless otherwise specified. The bromine, which is not a carbon chain, bromine just has lone pairs. It's just plain old Br. There are no other hydrogens. So these guys here have a bunch of hydrogens. Either you condense them down to CH2 or you draw them out and whatnot. If it's carbon, you have hydrogens. If it's a halogen, you don't. Okay. So hopefully you can do some more practice, and we're going to steadily add a little bit more complexity as we go through here. Thanks, guys.